right, everyone at SciPy, welcome to your first talk in the general track. My name is Paul Ivanoff. Madikin and Gwen are the other program co-chairs, and Madikin will be in here later on, and we'll be sort of swapping in who's introducing talks. So our first talk today is Chris is going to tell us how outperforming NumPy is hard. Let's give him a hand.
Good morning, everyone, and thank you all for coming today. So a little bit about me before we get started. I am Chief Technology Officer at Research Affiliates, a small finance firm located in Newport Beach, California. I've been programming Python since the year 2000. Back then I was working on a PhD in music composition and later was a professor of music technology. I did work there using Python for algorithmic composition and computational musicology. Since 2012, I've been building financial systems in Python, and that led me to create StaticFrame, an alternative data frame library built on an immutable data model. So that work in StaticFrame really gave me a long-standing passion for exploring performance in Python programs, from doing extensive profiling and optimizing Python code to writing my own C extensions to replace elements of Python code, to actually considering if I can make some NumPy things go faster, which led to this talk. So a bit about Python performance. As all of you probably know, Python is relatively slow compared to compiled languages. This is for many reasons, one of which is that all values are boxed in C Pi objects. Values are not contiguous in memory, and we must manage reference counts. So C extension using C types can be fast because they can avoid all of these things. With NumPy, we get C-typed arrays in Python, and that gives us excellent performance. But we come back to the question, can NumPy routines be optimized? Well, I think there's two things to consider. One is that some NumPy routines are implemented in Python, so maybe there's an opportunity there. And two, many NumPy routines do more than we need, and I'll explain what I mean. So, as I mentioned, some NumPy routines are actually implemented in Python. If you look at the source code for np.roll or np.linspace, you'll see that they are just implemented in Python. But they're all leveraging lower-level C routines, and as such, there's little chance a C implementation will be faster. So that's generally not going to be an opportunity. More promising is that a lot of NumPy routines are what I call sort of excessively flexible. Well, I mean, they're great, but the flexibility comes at a cost. So many NumPy routines will handle non-array inputs. They'll convert a list or a tuple to an array for you. They'll handle all dimensionalities of arrays, even though in my work I generally only deal with 1- and 2-dimensional arrays. They handle the full diversity of D types and support diverse array memory layouts, that is, non-contiguous memory. So all this flexibility comes at a cost. And we can ask maybe, just maybe, more narrow routines might be more efficient. And that's going to be a part of what we're looking at here today. So our test case is going to be finding the first true in a Boolean array. And this was a utility I needed in my work in StaticFrame. So given a 1D Boolean array, we want to find the index of the first true. Given a 2D Boolean array, we want to find the indices of the first true per axis. We want to be able to do this in both directions, and we want to be able to discretely identify the case when all values are false. I'm not the first person to look for a solution to this problem. We can see this Stack Overflow post from 10 years ago viewed 250,000 times, asking for how to get the NumPy first occurrence of a value greater than an existing value, which is essentially the same problem. Here, more explicitly, someone asks how to attain only the first true value from each row in a NumPy array. There's even an open issue in NumPy for finding the first non-zero element. And this issue has been open for, seems, well over 10 years, and is still open. There's 82 thumbs up there, so other people have been looking for this. Now, part of the reason it's probably not part of NumPy yet is that there's a few ways to do this with NumPy already. I would say that no NumPy function does exactly what we need, but two options are close. So np.argmax gets us almost there, and np.nonzero is also another way to solve this problem, and we'll look at both of those in a little bit more depth. So np.argmax will return the index of the maximum value in an array. If there are ties, the first index is returned. Well, that's not really our problem, but it's specialized for Boolean arrays to short circuit on the first true, because a true is the maximum value in a Boolean array. However, all false values return an ambiguous 0, so we have to call np.any to discover all false. So there's a little bit of a problem there. So here's an example of using np.argmax. We're going to create an array, all false but one true, and we see we can call np.argmax and get the index of the true value. Great. However, if we have an array of all false, it's going to give us 0, which is exactly the same as if we happen to have true in the first position. So this is a problem. np.nonzero is another solution. This finds all non-zero positions, not just in Boolean, but other types of arrays. It will return a tuple of arrays per dimension. It cannot short circuit because it has to search the whole array. So here's some examples of np.nonzero. So again, I'm going to create an array with one true in it, and np.nonzero is going to give me that tuple with an array. Now this is a lot more than what I need for my particular case. I just need the first true, so I'm going to have to index out that value as shown here. Now if we have many true values, we can use np.nonzero, and it's going to give us back all of the indices in there that are true, but again, that's more than we need. So how do these two operations perform? Well, I'm going to compare np.argmax plus np.any, because we need that any check, as well as np.nonzero. All right, here's a bunch of performance results. There's a lot there. I'm going to explain what you're seeing here, but we can start off by identifying the blue and the pink bars. So the blue bars are np.argmax plus np.any, and the pink bars are np.nonzero, and these are graphs of duration, so shorter is faster. And we see np.argmax outperforms np.nonzero in every scenario here. Well, let's talk about those scenarios. So we have 3 rows. Each row is the size of the one-dimensional array, from 100,000, 1 million to 10 million. We have 4 columns that represent different fill characteristics. So the first 2 columns have just one true value, set at 1/3 or 2/3 to the end. The column 3 and column 4 have 33% of the size of filled with true, filled from 1/3 to the end or 2/3 to the end. So if we look at these performance results again, we can see that in columns 3 and 4, np.argmax consistently, more significantly, outperforms np.nonzero. And we can have some intuitions about that. np.nonzero has to do more work. It has to collect all the trues, presumably using some sort of dynamically allocated array that has to grow and allocate memory. And so it takes longer when there are more trues. All right. So there are opportunities for improvement. The np.argmax, we have to call np.any to discover the all false scenario, and worst case requires 2 iterations, though we can short circuit. It does not search in reverse, which is something we were looking for. What about np.nonzero? Well, again, it requires 1 full iteration. It cannot short circuit. It collects much more than we need, and we must iterate over the results to find the first or the last, depending on what we're looking for. So in Python, there's many options for improving our performance of routines. We can look to a C implementation, we can use Python numba, we can use Rust via PyO3, we can use GPU libraries. For this study, I'm going to focus on a C implementation. Now, what makes a good opportunity for improving performance with a C implementation? Well, the key thing is that the core routine has to be done without PyObjects. If we're using PyObjects in C, we're not really going to get better performance, and I'll show you that a bit later. Even better, if we can operate directly on a C array, we have a very easy way to go back and forth between Python because we can always wrap that array within NumPy or pull it from a NumPy array. All right, so we're going to implement first true 1D as a C extension. It's going to be a function that takes 2 arguments, a NumPy array and a Boolean, and we're going to evaluate each element and return the index of the first true. Seems relatively simple. If we have no true, we'll return -1. And the code for this can be found in the npbench repository. I'll have this link at the end as well. Okay, so let's define a C extension. This is it, the smallest C extension you've probably ever seen. Maybe not, but probably. So I'm skipping all the includes here. That makes it a little bit shorter. Then we create a PyModule.def struct, and we assign a couple slots there, including the name of the module. And then we're going to create a C function called pyinit npbench here. And this function is going to import array, which we need to do for the NumPy C API. We're going to create a PyModule object, giving it the struct we defined earlier. We're going to add a string constant version to that module, check for errors, and return our module. There, the smallest C extension module you've ever seen, though it doesn't really do much. So if we want to add a function to this module, we can define a simple C function to parse our arguments is what we're going to focus on first. So this function, firstTrue1AD, is using a standard signature for a Python C-level function, and it's just going to take a tuple of args. If we want to take quargs and other things, we have to do more complicated stuff. We're not going to do that today. We're going to define two variables for our NumPy array and our forward indicator, and then we're going to use the all-powerful pyarg parse tuple to assign values out of the tuple into those variables. If this fails, we have to return null. We're going to have our implementation, and then ultimately, we're going to take a C integer type and give it to pylong from size t to get back a nice py object. So that's the outer scope of our functions that we're going to look at here. Now, to add this function to the module, we need to define an array of PyMethodDef structs, which we're doing here, naming the function as it's seen in Python and linking it to the function in our C code. And then we just add that to our module definition by assigning it to the method slot. Okay, so we've done it. We've created a C extension that has a C function, and we're ready to explore some implementations. Now, a key piece of this is reading elements from an array in C. And this should be pretty straightforward. You're probably thinking there's probably one good way to do this. Well, there's at least four, and there might be more. In one case, we can read PyObjects from arrays. In another case, we can cast data pointers to C types. We can use NPY-iter, or we can use raw C arrays and do pointer arithmetic. We're going to look at all of these approaches. We'll start with working with PyObjects. Now, this is counterintuitive. I said you get good performance by not working with PyObjects, but I think this gives us a useful baseline. So how do we read PyObjects from arrays? Well, we're going to see that. We're going to put some constraints. We're only going to process 1D arrays to make this simple. We're going to use pyArray getPointer1 from the NumPy C API to get a pointer to the element. We're going to use pyArray getItem to convert that to a PyObject. And then we can use the Python C API PyObjectIsTrue to evaluate that element. Because we're using PyObjects, we have to manage reference counts, which adds to the overhead of this approach. Okay, so here's our function. In the beginning, here's our function signature. We're going to parse the args, as I already showed you, and then we're going to establish a constraint. We're going to say, if you're not one-dimensional, I'm just going to raise an exception. And this is a really excellent way to reduce the complexity of your extensions by just not handling things you don't want to deal with. Then we can move on to the implementation. So first off, we're going to get the size of our array. We're going to create an integer I to track our index, and we're going to have a variable element for our PyObjects. If we're going forward, we're going to iterate over each index in the array, and we're going to use pyArray getPointer1 to get the pointer. We're going to use pyArray getItem to extract a PyObject, and now we have a PyObject at element. We can use PyObjectIsTrue to evaluate if it's true. If it is, we're good. We found what we were looking for. We have to decref that element, and we can break. Otherwise, we still have to decref the element, and we go on. We're getting a new reference every time, and we have to decref that reference every single time. Going in reverse is essentially the same. We're just going to count down in the opposite direction. We're going to use the same routines to get our PyObject. We're going to evaluate if it's true. Again, we have to manage our memory with a decref. And then finally, we're ready to return an integer. Now, if I is less than 0 or I is greater than equal to the size, we know we did not break. So we're going to set the value of I to -1. And then we're going to convert that C type to a PyObject with pylong from size t. How does this perform? Well, we can see our implementation is the blue bar there, and this is firstTrue1D getItem. And we see it's not great. It's really bad. In fact, in some cases, pyargmax is 2 orders of magnitude faster than what we just implemented in C. So this should reaffirm for you that just putting it in C doesn't make it go faster. This is roughly equivalent to what we would see if we had just implemented this in Python. So we haven't beat NumPy. Let's see what else we can do. So what if we use C types instead of PyObjects? So we notice that we get a pointer to the element in the array, and we can use that. So now we're going to only process 1D arrays, and we're going to limit this to Boolean arrays. That's going to make it easier for us to cast the type. We're going to use pyArray getPointer1 to get our pointer, and we're going to cast it. We no longer have to use the Python C API to evaluate it, and we don't have to do reference counting. That's a strong advantage. And even better, if we can release the GIL over the core loop here, which I'm not going to show today, but in some situations can also help if you happen to have some multi-threading going on. All right, here's our function signature, pretty much the same as before. We're going to limit to one-dimensional arrays, and now we've added a new constraint. We're only going to handle Boolean arrays. If the caller gives us a Boolean array, we're just going to raise an exception. Let them solve the problem. I don't want to solve it in my C code, and this is a great way to do that. Okay, moving on to the implementation. Again, we're going to get the size, and we're going to get an integer I to track our index. If we're going forward, we're going to iterate over the positions in the array. And here now, all we have to do is call PyArrayGetPointer to get the pointer from the array. And we've already assured ourselves that this is a Boolean array, so we can cast that pointer to a NumPy bool pointer, dereference it, evaluate if it's true. If it is, we break, and our I is in the right position. Reverse, basically the same. We're going to do the same thing. And then finally, if we did not break, our I is going to be less than 0 or greater than or equal to size. We're going to set that to -1, and again, return our Py object. So this has to be faster, right? Well, it is. So the blue bar was what we were doing before using Py objects. The purple bar, number 2, is the new implementation that we've done. And we see that this is a lot faster. So that's great. Let's zoom in on those 3 values. So now we see that our implementation using getPointer is pretty good. We're starting to outperform np.nonzero in a few places. But we see np.argmax even plus np.any is still a lot faster. So let's go on. What else can we do? Well, if you look within the NumPy C API, there are some other options, some that are very clearly labeled, like npyiter. So npyiter provides a common iteration interface in C. It supports everything NumPy can handle, all dimensionalities, d-types, memory layouts, and performs stride size pointer arithmetic in the inner loop, which is going to be pretty fast. It does require more code, and it does not support reverse iteration, so it doesn't really solve our problem, but let's see what we can do with it. So here we have the similar outer constraints of our function. Again, we're going to limit it to one-dimensional arrays. Again, we're going to limit it to Boolean arrays. And we can go on to the implementation. So to use npyiter, we have a family of functions that work together. We call npyiter new to get a dynamically allocated iter object that has a bunch of configuration there. If it's null, we have to return a null. It can fail. And then we can use more npyiter functions to get stuff out of this iter object. So we're going to get our iter next function pointer. We're going to get the data array pointer. We're going to get the inner stride array pointer, the inner loop size pointer. There's a lot of setup. And then finally, an integer to track our position. All right, we're ready to use this thing. So we're going to have a do while loop that calls iter next on iter. And then we can dereference our data pointer, our stride pointer, our inner size pointer, and then we can have our inner while loop here that counts down on the inner size, and we can evaluate our data pointer. We already know that this is Boolean, so we can just dereference that pointer, evaluate if it's true, and if it is, we can jump to the exit, deallocate our iter object, and then hand back the caller a Py object. If not, we can continue through our iteration. Finally, if we did not exit, we know we haven't found a true value. We can set the value to -1. All right, how does this perform? So the implementation with npyiter is the purple bar, number 2 there, and we see that it's consistently slower than what we were doing before, which shouldn't entirely surprise us. There's more overhead, we're using dynamically allocated memory, and we're just doing more stuff. This routine is more general, and we can see that it's going to be a little bit slower. We also see that it doesn't help us get any closer to np.argmax. So we got to go on. Now, what if we assume array contiguity? We saw in the npyiter example the use of pointer arithmetic in the inner loop, and I have a hunch that that's going to get us much closer to a high-performance solution. So we're going to assume array contiguity as an additional constraint on our function. We're going to use PyArrayData macro to get the pointer to the underlying C array, and we can only do that if we have contiguous arrays. Then we can advance through the array with pointer arithmetic. All right, let's see how this looks. Same outer function, same constraint, one-dimensional, Boolean, and finally we've added a new constraint to ensure that the array is contiguous. Again, if the user has given us a non-contiguous array, we just fail and let them figure it out. They can give us a new array, they can handle it. All right, on to the implementation. So here we use PyArrayData to get us the raw underlying C array of the NumPy array. And we can only use this directly if we know it's contiguous and we know the type, so I can cast it directly to a Boolean array, and now we have a very nice Boolean array. I'm going to get the size, I'm going to create integer to hold the index position, and some other variables for an active pointer and the end pointer. If we're going forward, we're going to assign the array buffer to the start, we're going to get the end pointer, and then in a while loop, we're going to walk through each of these elements and evaluate if they're true. If they are, we break, otherwise we increment p. This seems about as simple as we can get. Going in reverse, we do the same thing. We iterate through the results. We dereference p. If it's true, we break. We decrement p. Finally, if a break was encountered, we can use our pointers to calculate where the I is and then return a pi object to the caller. This has to be the fastest approach, right? It's not. So if we look here, our new approach is bar 2. This is the purple bar. And we can see that it's a little faster than bar 1 using the simple get pointer approach, but not a lot faster. And we can see that np argmax plus np any is still, well, frankly, really outperforming what we're doing here. So how is this possible? How is np argmax and np any still faster than what I imagined was the simplest thing I could do, pointer arithmetic on a contiguous array? Well, the answer is SIMD, single instruction, multiple data instructions. So SIMD's been around for a while. One of the oldest implementations of SIMD SSE has 128-bit registers. And if we're processing Booleans with that, 16 one-byte Booleans can be processed in one instruction. That's a huge advantage. More modern AVX 512 permits processing 520-bit registers in a single instruction. So this is true vectorization, and this is a pathway to excellent performance. Now, if we dig through the NumPy source code and try to find the SIMD bool argmax implementation, we can see it here. And I know this is really small. I'll zoom in a little bit in a second here. But this function is taking a raw NumPy Boolean array like we had. So we got that far. And then it's establishing some step sizes, v step and w step. And then in a loop, it's iterating over those step sizes, doing a bunch of stuff, which I'll talk about in a minute, and then evaluating if a non-zero was found. If a non-zero was found, it breaks out and then proceeds with element-wise iteration. Okay, so what's all that stuff that I skipped over? Well, we can see here that we're loading data from the array into our SIMD registers. We're doing that 4 times for different segments. Then we're comparing those registers to a 0 vector to essentially find any non-zero values. Then we're coalescing these values using subsequent AND operations on each of those, and then finally resolving that to a number. If that number is equal to the max number for the type, that means a non-zero was found, if it's not equal, sorry, and we break. So what we really do here is a kind of forward scan to discover truths. Now, SIMD is hard in C. Other languages support is probably easier, but I'm not prepared to implement SIMD for my own extensions, and I think it's a pretty challenging thing to do. But one observation we see here is that SIMD reduces loop iteration. So what about loop enrolling? Now, everyone here probably has heard about loop enrolling, but we're kind of suggested against it because our compilers are supposed to be smart and maybe this doesn't help. But let's try it. We can reduce for loop iterations, and it may actually optimize CPU branch prediction, which is why it's used. So again, we're only going to process 1D Boolean contiguous arrays. We're going to use pi array data to get the underlying C array, and we're going to advance through our array with pointer arithmetic unrolling units of 4. We'll use LLDiv to get the quotient and remainder, and that remainder will give us any additional element-wise looping we have to do. Okay, so I'm not going to show you the whole code for this, but I'm going to show you a key example of the forward iteration. So again, we're going to get our starter and pointers, and in our while loop, we're going to do less looping. We do less looping by just spelling out 4 operations. And this looks kind of silly, but you'll see it works. If we don't fit within a 4-size unit, we have that remainder, and then we need to do element-wise iteration. So how does this perform? So we can see number 3, the red bar, loop enrolling works. It gets us quite a bit faster than what we were doing with first true 1D pointer. So that's pretty cool. but it's still not as fast as np-argmax. So where can we go? SIMD looks ahead for true values. There's two options I can think of just using standard C to do a similar operation. One is to use memcmp to compare raw memory to a zero array buffer. Another is to cast 8 bytes of memory to an unsigned integer and compare that to 0. This efficiently forward scans 8 one-byte booleans, and upon discovery of true, we fall back on element-wise iteration. So it turns out that the unsigned integer casting is a little bit faster. So we're going to do that. We're going to do the same thing. We're going to do forward scanning of 8 one-byte booleans by casting to a uint64. And then we're going to jump ahead in units the size of NPY uint64. This gives us less code and actually better performance. So again, we can see the code here. Here's the key move where we cast our pointer to an unsigned integer and dereference it, evaluate if it's true. If it is, we break, and then we fall back on element-wise iteration to discover our actual position. And finally, we've done it. We've outperformed we've outperformed NumPy. We see number 3, the bar number 3 here outperforms np-argmax in every case here, though you might notice as the scale grows, our outperformance diminishes. So at a certain scale, I think np-argmax the SIMD is gonna keep up with this. Here's the big picture in logarithmic space. And notice that we have sort of 3 levels, 3 orders of magnitude here of performance. The slowest is using pi objects. A bunch of the solutions that we had using C are around the middle. And at the bottom, at almost approaching 3 orders of magnitude improvement is what we get from using our forward scan approach. So hopefully I've convinced you outperforming NumPy is hard. When considering implementing something in C, recognizing when the work can be done with C types is critical. Implement limited function. Only support the needed dimensionality, only support the needed D types, require contiguity when you need it, and constantly test your performance. Thank you for your attention. I want to give props to SlideDiv, which I use to produce these slides. If you haven't used it, check it out. The code for this project can be found there. Packaged wheels of these functions, first true 1D, first true 2D, are available with the ArrayKit package. And this work was done to support static frame, which you can learn more about there. Thank you for your attention.
Thank you, Chris. As promised, Madikin is here with a floating mic if you have a question in the room. And then from Slack, you can use the Track General channel to ask questions there. And so we have a question there, which is David asks, why use np-any instead of just indexing to the second element to see if the element is false, and then you don't have to walk the whole array again.
Yeah, that's a great alternative approach. I guess I was thinking I would use np-any first, but yeah, you could definitely do that. That's a fine approach.
Okay, somewhat of a fundamental question. Why would you be trying to outperform a function that's already in NumPy? I think that when we're making C extensions, we usually want to do something that would be several NumPy steps, and we want to fuse it into a single step.
Sure, understood. In this case, I felt the NumPy options were just insufficient, as I pointed out, both argmax and the other one requiring some additional steps. So that kind of led me to explore. But I agree, kind of focusing on one function is a very narrow case.
Okay, we've got a couple over here. I saw somebody back here first, I think, and then I'll come back up to you.
Thanks a lot first for the presentation. I was wondering, for people that are not so experienced with C programming language, they might feel more comfortable when using Numba library, for example. From your experience, when do you think it's better to switch from Numba to a C extension, or if there is any advantage?
Yeah, I'm afraid I can't answer that too well. I've been focusing on using C and C extensions. So a larger scope of this, I imagine actually bringing in Numba and other things into the mix, but I only have half an hour. So, but that's Numba and Cython surely are alternative ways to solve this problem.
Okay, we got 2 more over here, I think. Oh, okay. I think this is going to be our last question, but you can keep asking in the Slack, and I
I'll be
encourage
available.
our speaker. So in track-general, that's where we're going to have the Q&A for all of the general track questions. You can post in there, and you can have follow-up conversations with the speakers there.
C is good, and then there's something else, C++. So can the equivalent thing be done with C++ in the system? It basically is,
Yeah, absolutely. Absolutely, yes.
Okay, thank you. Let's thank our speaker once more.
Thank you, everyone.